Hey guys, so in this video I want to talk about a little trick that you must know how to apply in order to solve certain types of energy questions. Let's check it out. So this has to do with the fact that gravitational potential energy is relative. Gravitational potential energy is relative. So what do I mean by that? Well, in energy problems it says here, what matters is not an object's initial height or final height, but instead the change in height. So the actual heights don't matter. What matters is the change in height. And you might remember, for example, that the work done by gravity or by the weight force is negative delta U gravitational, which gives you negative mg delta H. And what matters here is delta H and not the actual H's. Okay? Now it says here, if you know an object's change in height, then you don't really need to know the exact initial and final heights, because you can set the ground level, you can set the lower heights, you can set the ground level, which is where H equals 0, to be at the lowest point in the problem. Okay, and I'll show you an example of this. Here, in a situation like this, you don't know the distance between the lowest point, B over here, and the ground. Okay, but if you don't know this, what you can do is you can say, well, I'm going to call this to be H equals 0, and since the gap between these two is 10, then this will be H equals 10. Effectively, what you're doing, we can think of this as you're moving the ground up, right? But effectively, what you're doing is changing the relative reference level of gravity. So it says here, gravitational potential energy is relative, meaning it depends on, an arbitrary, meaning up to you, you get to pick where, reference height. And the idea is that 0 is your reference height or ground level, right? This is your reference height right here. All the other heights depend on this. But if I wanted to, I could have made this 5. And then this would have been 15. It's just that this is more complicated for no reason, okay? So you can do this in two situations. One, when you don't know this here, when you don't know the height between the floor and the lowest point, you have to do this. But you could also do this in a situation where you knew it, but you just wanted to simplify things. I'm going to draw this real quick just to show you, but you don't have to draw this because you need the space. Let's say you knew that this was a 10, and then you knew that this was a 50. Since the lowest point is right here, you could actually, instead of making this height here a 10, right, you have 0, 10, and 50, you could make this the 0, because it's the lowest point in your diagram, and this part doesn't really matter. But if this is a 0 instead of a 10, I reduced 10 from here, then I have to reduce 10 from here, and this would become 40, because the gap between these two here is 40 meters, okay? In this situation, I didn't have to do this. I did this so that the problem was a little bit simpler. Now that my height here is 0, my potential energy is 0, and I have less types of energies, okay? Here, I had to do this, all right? So this isn't just a trick to make problems easier. In this case here on the left, you had to do this so that this problem was solvable, all right? So like I said, I hope you didn't write this. I was just showing you a different situation, but this is the most important case when you absolutely have to do this, okay? Just to complete here, where H equals 0. So the line where H equals 0 is up to you. You can move that, and if you do, you have to adjust other things. Once we've done that, then it's pretty simple. It says here, if the roller coaster cart moves at a point A with 20, or passes that point with 20, so VA equals 20, calculate VB. Okay, so we're going to use conservation of energy equation from A to B. KA, UA, work non-conservative, KB, UB. There's kinetic energy and potential energy because I have a velocity and a height. There is no work non-conservative because we're going to, since there's no information regarding an external force, you're not pushing it, there's no engine, and there's no friction, we're going to assume that this doesn't exist. There is kinetic energy at point B. In fact, I want to know the speed at point B, If B is lower than A, there has to be kinetic energy there. There has to be a speed. But since I raised my ground level from here to here and made that be my H equals 0, there is no potential energy at point B. All right, so I end up with just these three types of energies. Let's expand this. Half mv VA squared plus mgha equals half mvb squared. The masses will cancel, and I'm looking for VB. So I just have to multiply the whole thing by 2 to get rid of this half here. This will be VA squared plus 2GHA equals VB squared. So VB is the square root of VA squared, which is 20 plus 2, gravity 10. And the height of A is 10. All right. So this is going to be the square root of 600, which is 24.5 meters per second. Okay, that's it. So that minor trick now allows us to solve a few other problems that we couldn't do before if we didn't know this. A quick note here, if you do not set H to be equals to 0 at the lowest point, points below H equals 0 will have negative potential energy. What's up with that? Well, let's say I'm going to redraw this situation here. Let's say I got A here, B here. Let's say this gap here between these two is 10 meters. Let's say for whatever reason you wanted to make this H equals 0. Well, this point here is 10 meters below that, so this has a height of H equals negative 10. Okay, we'll have a negative potential energy. The reason I'm telling you this is so you know that it's okay to have a negative potential energy. Negative potential energy just means you're below the arbitrary reference line where H equals 0. In fact, gravitational potential energy is the only type of energy that could ever be negative in terms of mechanical energies. Okay, so it could be negative, and that's fine. All right, you just have to, once you move the H equals 0, you have to adjust everything accordingly. Now that we've talked about this, we're going to talk about some pendulum problems, because in most pendulum problems, what's going to happen is you won't know the distance between the floor and the pendulum's lowest point. So let me show here. Here's a pendulum. This thing is just a mass at the end of a string, and the string is fixed here so that this thing can oscillate from left to right. Okay. The points of interest are the beginning here. Let's say it starts here at point A, at the maximum. We call this the maximum amplitude, the maximum height on the left. B here at the bottom is the lowest point. That's important too. And obviously C all the way at the other end here is important. If I release this from a certain height up here at A, it's going to reach the same height over here at C. Same thing with the angles. Whatever initial angle I start here with, I'm going to have the same angle all the way at the other end because of conservation of energy. Wouldn't lose any height or any angle unless there is some sort of resistance. Okay, so the idea with these pendulum problems is that you typically won't know this gap here. And because you don't know this gap, you have to, instead of making this your H equals 0, you're going to make the lowest point in the pendulum your H equals 0. Okay? So it will be the pendulum's lowest point will become your reference 0. Okay? So it says here a pendulum is built from a 2 kilogram bob. That's this part here. So I'm going to say mass equals 2. And a rope that has a length L. Let's do this. Length L equals 3 meters. All these units are SI units. We're good to go. It is attached to the ceiling and it is pulled until it is 1 meter above its lowest point. So it's pulled until it's 1 meter above its lowest point. We're going to make the lowest point H equals 0. Therefore, this H here, H initial, will be 1 meter. Okay? If the bottom is 0, and the gap between the bottom and the top is 1, then the top is 1. All right? We want to cut, and then it's released, it's pulled, and then released. It's implied here that it's released from rest. Okay? We want to know what is the pendulum's maximum speed and the rope's tension at the bottom. Notice one last thing here. It says it's a light rope. This just means that the mass of the rope is 0. And that's how all pendulum problems will work, okay? So pendulum's max speed, I'm gonna call that Vmax. Now, where do you think this maximum speed happens? At A, B, C, or maybe somewhere else? And I hope you're thinking B, because that's the answer, right? So the velocity will be 0 at point A. Let me just say that V initial equals VA, which is 0. And VC will be 0 as well, because it stops, and then it goes all the way to the other side, stops, right? So the maximum speed will be right at the middle of that motion, which is at point B. So Vmax is the same thing as VB. This is a curved path. That's why we're talking about this now. And it's a curved path problem where I'm going from A to B, right? I know the initial height of A, and I want to find out the speed at B. So I'm going to write an energy equation from A to B. Kinetic at A, potential at A, work non-conservative, kinetic at B, potential at B. There's no kinetic energy at point A. There is potential energy at point A because it has a height of 1 meter. Work non-conservative will be 0 because the work done by you is 0. You're just watching this thing, and then there's no friction, right? There is kinetic energy at point B because it has its speed, and that's the speed we want to find out actually. But there's no potential at point B because since B is the lowest point, we raise the floor so that H equals 0 matches with B. So the height of B is actually 0, right? HB equals 0. All right, so very straightforward. We have MGH on the left, MGHA, and half MV squared B on the right. The masses cancel, and the final velocity, or the velocity at the bottom, will be the square root of 2GH, right? Once again, the square root of 2GH shows up. Irrespective of the path you take, as long as you drop a height of h with no initial speed, your final velocity will always be this. So let's plug in numbers now. 2, 10, the height's 1. So I get the square root of 20, which is roughly 4.5 meters per second. Okay, that's it for part A. There is a part B here, and let me try to make it fit here. I want to know the rope's tension at the bottom. Okay, so tension is a force. You can't find forces using the energy equation because it doesn't have forces anywhere. If you look through all the components of an energy equation, there's no force. We're going to find force like we've always found force, using F equals ma. Now, this is going in a curved path, so it's going to be sum of all forces in the centripetal direction equals mac. All right, I'm going to over here draw, I want to know the tension at the bottom. At the bottom, the block is like this, and the rope is completely vertical since this thing is exactly at the bottom. The forces are mg going down and tension going up. The acceleration is always towards the center in a circular problem, which means that the tension is greater than the mg. All right, so this is going to be positive because it's towards the center. This is going to be negative because it's away from the center. So let's do this. I have positive t plus negative mg equals mac. And what we're looking for here is the tension. Now, to solve tension, I need mg, which I have the m, and I have g, obviously. I have m, but I need ac. I don't have ac, but I can replace ac with v squared over r, and that I have. So t will be m. Instead of ac, I'm going to write v squared over r, and then removing this over here, plus mg. T equals, the mass is 2. The velocity or speed is 4.5 squared. Radius. What is the radius of this circle here? Where do we get that from? I hope you see that the radius comes from the length of the rope. The length of the rope gives you the radius of this partial circle. It's not a complete circle, but it doesn't matter. It still has a radius, and the radius is the distance from the middle and the edge, which is L. So this is a 3. The mass is 2, and gravity we're going to go with 10. Now, if you have this and you plug in all your numbers, you get a, ooh, I don't have that. This is going to be 2, 20, 3 plus 20. This is 40, 13.3, 33.3 newtons is the force. The mass is 2, so mg is 20, and this is 33. It's greater than 20. It's greater than mg as we expected. So that is the final answer. I hope this made sense. Let me know if you guys have any questions.